In this video, we're going to talk about Simpson's rule. It's another approximation method similar to the midpoint and trapezoid rules, where instead of using rectangles and trapezoids, we're going to be looking at the area under a given parabola. So, what does Simpson's rule say? Simpson's rule, okay, so it's the same basic startup just as we had before. You have a function f of x that's non-negative. You choose some degree of approximation, so you want to partition your interval from a to b in a similar manner, just like we had before, except now we're going to require that n be an even integer, because otherwise the construction and the method that we use here won't work. I'll explain here in a second. But the idea is that you have this uniform partition, delta x, which is the length of the interval divided by the number of partition points. And for simplicity, we're going to denote delta x as h, which is the notation the book uses. But if you have this function f that's drawn here in my pen, and you have a and b, and we want to integrate from a to b, we will denote a as x0 and b as xn, in this case n is equal to 6. And when we divide up into n pieces, we're going to construct parabolas. So the first 3 points from these partition points will form my first parabola. And then for the next 3 points, we're going to make another parabola given here so that these two parabolas have the same endpoint, which is this point of the curve. And then you keep doing that. You start connecting parabolas together. And then here, my third parabola will start here and is formed by this one, and we find a parabola that goes through those 3 points. Remember, it takes at least 3 points to create a unique parabola. Okay. So, just like finding the area of a trapezoid and finding the area of a rectangle, we are going to be finding the area under this parabola down to the x-axis. Okay, so to make the calculations easier, let's just focus on one parabola at a time. For example, the leftmost parabola given here. I tried to draw the parabolas in my picture with the pencil, but I wasn't very successful. But the idea is that you have a curve and then you draw a parabola through these points, and roughly speaking, the area under the parabola is equal to the area under the curve up to some error. So focusing on this parabola, what we can do is, to make the calculations easier, is to do a horizontal translation where this midpoint, the middle point between these two guys at x1, this x1 can be shifted over to 0 so that x0 is on this side and x2 is on this side. And remember, the distance between any two given partition point, well, two consecutive partition points, is equal to delta x, which is what we denoted as h, which means that this is equal to negative h and this is equal to h if we translate x0 to 0, or excuse me, x1 to 0. Okay, so you've moved this parabola over to a symmetric interval, or about the origin, and this gives us some parabola, which I define as y equals ax squared plus bx plus c, and we want to integrate, right, because we want the area under the curve. If you do a horizontal translation, it doesn't change the area under the curve, and the reason you do this is because this calculation becomes much easier if you make it symmetric about 0, because look at what happens. You integrate this parabola, or this quadratic, from negative h to h. And if you use some tricks, you'll see that this integral is equal to 2 times integral from 0 to h, ax squared plus c. The trick that I used here is that if you do this piece by piece, if I just integrate ax squared, this is an even function, which means all I have to do, it's an even function about a symmetric interval. which means if instead I choose to put 0 here to h, I would just double this amount. And the same logic applies here for c, because a constant is an even function. And about a symmetric interval, you just replace this with 0, put a 2 here, and that's how I get this. And so the next question is what happens here, because it's no longer on the right-hand side. Bx is an odd function about a symmetric interval. And if you integrate an odd function about a symmetric interval, it's going to disappear. You get 0. If you don't believe me, you can just do this piece by piece, and eventually you'll see that this is the calculation that you end up getting. This integral evaluates to 2 times h cubed over 3 plus ch. And then shifting some terms around, we can pull out a 3. So here I pulled out a 3 here. If you pull out a 3 from, what have you? What did I do? Oh, sorry. You push the 2 through. So the 2 goes here, and you have 2ch. And if you pull out a 3, then I have to replace this with a 6 in order to balance the equation. So I have h over 3 times 2ah squared plus 6c. And the motivation for writing it this way will be evident later. But basically, this h represents delta x, and then you have a 3 here. And then the stuff that's inside the parentheses will involve terms involving f. Okay. I should tell you right now I'm feeling a little bit sick and under the weather. I don't know what's going on, but I'm getting some pretty bad vertigo. So it's taking a lot of strength not to throw up during this video. But I think I'll be okay. It may be a little bit rough, but the notes are good. So visually, what are we seeing here? You're integrating this parabola over the interval from negative h to h. You have these 3 points that are the same 3 points up here, except you just translate it this way so that x1 is at 0. And this is the picture you get. So this represents this shaded region. So what are we going to do with this? We don't like this A, B, and C business, because what are A, B, and C really? I need to be able to compute something, right? I don't know what they are. But we can establish a system of linear equations, because if we denote this point as negative h comma 1 or y0, and this point as 0 comma y1, and this point h comma y2, then if you plug in these inputs, negative h0 and h, into this function that's over here, that will give you the corresponding y0, y1, and y2, which is what I've written down here. y0, this guy, is equal to this equation evaluated at negative h. So you just plug in negative h wherever you see x, and this is what you get. If I plug in 0, this term dies, this term dies, and what I'm left over with is c. So I have y1 equals c. And then y2 is, you just plug in h. It's ah squared plus bh plus c. Now, if I add some of these y's together in the following way, you can do this algebraically to see it for yourself. If you add y0 to 4y1 to y2, you'll see, and just arrange the terms in a way, you'll see that this actually comes out to be 2ah squared plus 6c, which is what we had on the previous page. That's equal to the area under the parabola, which means I can make this substitution and have h over 3 times this sum that I have here. Remember, this was here earlier, so now I'm just substituting it with this. And the reason I like this is because those y's can be written as f evaluated at a point. Because remember, this parabola was my initial parabola translated to the left or right so that it was symmetric about 0. But, well, okay, not symmetric about 0, but that middle point gets mapped to 0. So, what does this mean? The y values don't change when you translate left or right, which means that I can just plug in f of x0 here, f of x1 here, and f of x2 here. And then I have area under the parabola. But we need to do this for all other parabolas. And the calculations is pretty much the same, except now you're taking x2, x3, x4, and you're shifting it in a way that x3 coincides with 0. Let me flip back to the original page so you can see what I'm talking about. So we took care of this parabola, now we're at this one. So remember what we did. This point, this middle point at x1 got shifted to 0. Now we're looking at this parabola, and you take x3 and you're shifting it to 0 and doing the exact same thing, the exact same calculation. And for the third one, you'll take this midpoint that's at x5 and move it over to 0. So in general, your parabolas will have these areas, h over 3 times this sum. Notice how we start at y0 and go up to y2. And this area, h3 over 3, starting at y2, this guy, starting at y2 up to y4. And then the next area will be h over 3, starting at y4, going up to y6, so on and so forth. And then if you want the total area, which we denote as Sn, you just add up all these guys together up until you get up to yn. And I screwed up here, unfortunately. No, wait, nope, that's right. Never mind, this is right. So you have this sum which approximately equals the integral of f of x from a to b. Okay. Now, just like we did in the trapezoid rule video, we can rearrange some of these terms together because when you want to compute this, it may be easier to see the formula that way. But if you'll notice here that we have 1 y0, we have 4 y1s, which go here, and this y2 shows up here and it shows up here, which means I get 2 y2s, so I put that down there. And then we go back to 4 y3s, which go here. We have y4, and then the next one will have another y4. So we get 2 y4s. And you continue this pattern on and on and on until you get to the end where we'll have 2 yn minus 2s. One shows up here, and then one shows up over here. And then you get 4 yn minus 1s, and then 1 yn. And each of these y's are just f evaluated at that partition point. So if we replace yi with f of xi, this is the usual way that you will see Simpson's rule. So Simpson's rule is this equation that we have written here. Sn is equal to this, which is roughly equal to the integral. I went through that pretty rough, but I think it's good enough. You didn't know I was a poet as well as a math teacher, did you? So we look at the example that we talked about with the midpoint rule and the trapezoid rule, and we're going to now approximate it with the Simpson's rule. Except remember, we did 5 last time, but with Simpson's rule, you have to choose an even n. The reason that you have to choose an even n, in case I didn't explain it earlier, is that you need, if you have an odd number, like if you have x7, for example, you're going to have this extra point that hangs out over here, and you need these 3 points to create a unique parabola through them. And then you connect them tip to tip, or dot to dot, if you will. So if you have another one here, then there's a little bit of overlap or some spillover that you don't want. You want an even number. Okay. Man, I'm dizzy. You have to approximate this with S10. So in this case, n is equal to 10. So if n is 10, a is 1. Remember, this is a, this is b. There it is. And then if you calculate h, which is delta x, you have 2 minus 1 over 10, which is 0.1. which means my partition points are starting with 1, and then you just add 0.1 every time. So we have 1.1, 1.2, 1.3, all the way up to 2. And then you just plug all that stuff in to the formula that we have at the bottom of the previous page to get S10. You have delta x over 3, f of 1 plus 4 f of 1.1 plus 2 f of 1.2, blah, 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 blah. And then eventually you have to write all this stuff out. And I'm kind of being a little bit lazy here with putting the dots because that could create some confusion, maybe explicitly. Okay, when you're doing this on your homework, you should definitely write out all these terms, otherwise you're going to make a mistake. But just to illustrate, the pattern here, I've written out in whatever, I've just written it here. But trusting my math abilities that I can punch all this stuff into my calculator, we see that S10 is roughly equal to 0.693150. And if we're interested in comparing this to the midpoint rule and trapezoid rule to see how good of an approximation this is relative to those two other methods, I've written down their approximations here. The midpoint rule gives 0.692835, trapezoid gives 0.693771, and then I've rewritten S10 here. But if you punch in the known value of this integral, which is natural log of 2, natural log of 2 is roughly equal to what your calculator will tell you, 0.693147. And you'll notice something pretty immediate here. M10 and T10 are, well, okay, let's start with M10. M10 is right in the first two spots down here. T10 is right or correct in the first three spots. And S10 is correct in the first four spots. And you got this 5,0 here, which is very, very close to 4,7. The point I'm trying to make here is that S10 is actually better at approximating than M10 and T10. You get closer to natural log of 2 with smaller n values. And we actually do have a way of characterizing that, or describing that, I should say. Because just like with the midpoint rule and trapezoid rule, we had error bounds. The Simpson's rule also has an error bound, which looks a little bit different from midpoint and trapezoid rule. But the error bound is actually better than those two guys. So let's look at it here. Error bound for Simpson's rule. So in Simpson's rule, you want to calculate the fourth derivative of your function. For midpoint and trapezoid, we just calculated the second derivative. But for Simpson's rule, you need the fourth derivative. So you compute the fourth derivative, and you want to establish that it is bounded above by some constant k over the interval of integration. Otherwise, you can't use this approximation, or this error bound. If this is satisfied, you have an upper bound for this fourth derivative. Then the absolute value of the error in Simpson's rule is less than or equal to that constant k times the length of the interval raised to the fifth power, so it's not third anymore, it's fifth power, divided by 180 times n to the fourth. And this n to the fourth is the reason why Simpson's is a better approximation. Because in midpoint and trapezoid, you had n squared, which decays pretty fast. But n to the fourth decays even faster, which means that you get a better bound for lower n, for the same n. Okay, let me rephrase that. For n equal to 10, you'll have 10 to the fourth here. In the other two upper bounds, you have 10 squared. And 10 squared is smaller than 10 to the fourth, so your error is going to be smaller for different values of n. So let's do let's do an example. So we have the integral that we had before. dx over x from 1 to 2. We want to integrate that. We got an answer, S10. Let's compute an upper bound for the error for S10. So the first thing that you should do is calculate the fourth derivative. So f of x is x to the negative 1. You take its derivative, which we've seen before, it's written here. We calculate the second derivative, which we've seen before, it's written here. And now we calculate the third derivative, which gives us negative 6x to the negative fourth, and then do it one more time to get the fourth derivative, and look at there. We have 24x to the fifth, negative fifth, or 24 over x to the fifth, if you prefer. Now take the absolute value of that function. The absolute value of the fourth derivative is equal to 24 over x to the fifth, and because x is between 1 and 2, to make the fraction bigger, you make the denominator smaller, which means that this derivative is bounded above by 24 over 1, which is equal to 24, and we can set k equal to 24. Identifying a, b, and n is the same as it was in the previous example. You have 1, 2, and 10 respectively, and now all you have to do is plug that stuff in. So absolute value of the error is bounded above by my formula. Put 24 here, put 2 here, put 1 here, put 10 down there. And this is what you get. Simplifying this, you will get 2 over 15 times 10,000, which reduces to 1 over 15 times 5,000, like I've written here. And 15 times 5,000 should be 75,000. Which is a pretty small error, 1 over 75,000. Okay, because I'm about to puke, let's go through this last example very quickly. Getting old sucks, that's all I have to say. How large must n be so that your Simpson's rule approximation Sn has an error no bigger than 0.0001. Okay, so again, you're approximating this. We know what A is, we know what B is. We just found out what K was in the previous page, which means that if I plug all that stuff in, I'll have this expression. But now I don't have n. I need to figure out what n is so that this fraction is bounded above by 0.0001, or 1 over 10,000. And if I ensure that n is chosen well so that this inequality holds, then I know my error will be bounded above by 1 over 10,000. Okay. Reduce this, or simplify it if you prefer. You'll have 2 over 15 times n to the fourth less than 1 over 10,000. Multiply both sides by 10,000, multiply both sides by 15n to the fourth, and you'll get 20,000 on the left, and then 15n to the fourth on the right. Divide both sides by 15, take the fourth root, and we see that the left-hand side is about equal to 6.04, which means that we need an n, integer n, bigger than 6. And remember, n has to be an even integer in order for Simpson's rule to work. So the smallest even integer bigger than 6 is 8. So n equal 8 will give us our desired approximation, which is pretty short, or not short, but a relatively small number for a pretty good accuracy. You know, it all depends on what you mean by pretty good, but 1 over 10,000 is pretty small. So that's all I have to say about Simpson's rule. Look in your textbook, look at those examples, go through them yourself, write down this problem by hand, and if I'm feeling well enough on Thursday, and if we're not all frozen because it's like -8 degrees, we'll do our quiz. If not, we'll do the quiz next week.